So from this equation, just like we mentioned, during this part, still same as solid mechanics. But the left-hand side, we will change to the Euler coordinate. So that means in the integral form, that will become to the control balance. So if we consider the space, this will become to the control balance analyze. And the right-hand side, basically still the individual particle, what kind of force they will have. One is like the body force. That will depend on in which field you are in. Most of the case, we are in the gravitational field. So this gravitational force we will consider. Recently, in some kind of electronic device is very popular. So if in some kind of electronic device, you consider this kind of electromagnetic field, that will similar analyze like the gravitational field, because in this field, the whole body they will feel this kind of force. So this is body force. Then another one is the surface force, or we consider like the contact force. This force usually is due to stress. So remember what kind of stress we have. Shear stress and
pressure.
So pressure is normal stress. So normal stress is related to the pressure. This is usually we are consider like the binary equation. We have a pressure term. That's the normal stress. So this part is a contact, and basically they will consider in the two directions. The normal to this surface, or there are the like the normal, and it's not normal, it's the perpendicular to this surface. If perpendicular to this surface, we become to the shear stress. Okay? So this is due to the stress. So basically, we want to talk about this stress because this stress we relate to your service force, and this stress, as we mentioned in the chapter 1, they are the symmetric tensor. So that means you switch these two index, then we get the same value of these two. That will be the set. And for this kind of tensor, you can find some kind of principal axis, okay? And usually they will correspond to the eigenvector and the eigenvalue, this kind of problem. Then for this force in the x direction, if we consider the front face, basically one square they have 6 sides, 6 surfaces. So if we look at this part, basically it's the side we can see. Usually we regard this as the front side. And also their direction is positive. For example, this direction is a positive x direction. This is a positive y direction, and this is positive to a z direction. And also x, y, z direction, how you decide, how you determine the x, y, z direction. Yeah, usually we need to use the right hand low. Okay, don't determine the x, y, z direction, just casual. Otherwise, there are some kind of a system that they will not follow the general rule. Okay, for example, like a rotation direction. Then, if we look the front side layer force, that will include normal stress and shear stress. In most of the cases, normal stress will contribution most. That's usually the pressure. Then for the slow motion velocity, that means your velocity is very small. That's correspond your pressure is small. Then they will be comparable. Usually that is low Reynolds number. Then your shear stress will be comparable with your normal stress. Okay. So from this case, if this full element is stationary or steady, that means they constant velocity. They don't have acceleration, or they are stationary. Of course, stationary, they will come to another case. If the stationary, do you have a stress? It's possible it's in the final exam question. If the flow become stationary, do they have a stress? Yes. You think yes? You think no? Okay. So basically, in the hydrostatic, what kind of a force you are considering? In your undergraduate, hydrostatic problem. Pressure. So pressure will relate to the normal stress. Because you don't have a motion. You don't have a motion, so flow doesn't have any motion, so they don't have a velocity gradient. So there's no shear stress in the stationary part because they don't have a velocity difference. As long as velocity without a gradient, that means shear stress doesn't play a role. But normal stress will become one of a force. So later on we will show if the hydrostatic, you only have a normal stress. Okay? So so that's one of a balance case. Stationary. Constant velocity. That means the equilibrium. That's the Newton first law, right? Newton first law is an inertial law. If a motion is with a constant velocity or stationary, unless external force, they will change this kind of motion status, or they will change their original status. Okay, so that's the Newton first law. Stationary. That's mean the balance. But if they have acceleration, they have external force, they will cause the acceleration, just like this. You have external force, no matter body force or no matter the surface force, they will cause the acceleration. So if they have acceleration, that means they have some stress difference. For example, normal stress from the front side and the back side, they maybe have a difference. And the difference is described by the calculus, by the differential form. This x direction difference is due to the distance, this part, dx, the difference. Okay? And I think this kind of free body diagram should taught in your undergraduate or maybe your high school already. Okay? Here I just sometimes like remind you this part. And from here, the dimension should be like we look the differential form or in the calculus. This should be the dx. And this volume should correspond to this part. So later on you can see you have two parts. This corresponds to the surface. And this part corresponds to the length difference. So similar, this force will correspond to the surface. And because we also need to consider the difference between the distance between these two surfaces. So we will get this value later on. So different surface, different this small area correspond to a distance. We will get a common term for this small value. Okay? So now we make our equation more easy to simplify. Okay, so from the equation 2.15, I think I just addressed, the x direction net force, basically we will see this side and this side for the x, the shear stress xx, just like this one. So this component is for this face. So we have a dz, dy dz, this kind of a surface. Similar for the shear stress. The shear stress in this surface dx dz, then we will consider the x dz, this one. So in the up and the down. Okay. So another one is a dx, dy is for this side and the other side. So basically, in these three sides, you can look the difference, the stress difference, and the distance correspond to this kind of surface area. And then all we get the dV, this term, so we can divide by the dV. So this force, we can write down like this stress difference. So stress difference will correspond to the force difference. And this force difference, if we use the previous index notation, we can correspond to the y direction and also the z direction. The different kind of force direction we become to the I, and we will summation the z direction. So z will correspond to the x, y, z. Then all the area we will correspond together. So here we will use this to correspond to the surface force. So we have a surface force and we have a body force. Then we can use this relationship. We write our Gaussian equation. External force correspond to the surface force and the body force. Okay, so momentum so far we are talking about the Newton's second law. But after this, we will use the assumption by the Stokes. That's the assumption of deformation rate. So after that, that will become to the Navier-Stokes equation. Okay, so momentum equation, sometimes people talk about is the Newton's second law, sometimes talk about Navier-Stokes, sometimes talk about Euler. That's depend on the different kind of assumption. Okay, we take a break.